Hi everyone, I'm Benjamin Zhu from CUHK Multimedia Lab. Today I'm very glad to be here to present my paper nuCraft, which is a high-resolution 3D semantic occupancy dataset together with a novel occupancy prediction model, VQ-Occ. Here is a paper's session information and a project page. If you are interested in the code, you can scan the QR code here. Firstly, the 3D semantic occupancy prediction task is about predicting the 3D structure of a 3D scene inside a certain fixed volume. In this 3D space, we need to determine each voxel's status is occupied or free. And if a voxel is occupied, we need to predict a semantic label. Previously, the major benchmarks for this task is Occ3D and Open Occupancy. They are all derived from the nuScenes dataset, but their resolution are quite limited. The most precise resolution of previous benchmarks are 0.2 meters, but usually in 3D object detection or 3D semantic segmentation, the resolution is usually much more fine. For example, 0.1 or 0.05 meters. So the 0.2 meters are not enough to replace the old-fashioned perception tasks and to achieve unified 3D scene understanding. Another problem is the nuScenes dataset faces very inaccurate annotations. For example, the equal pose of the nuScenes dataset is quite inaccurate, so we need to fix this problem. Here I show some errors and and wrong annotations of previous benchmarks. Here we can see that there are missing objects and noisy boundaries, and also incomplete geometries inside their ground truth occupancy. So all these problems hinders us from achieve the truly 3D scene understanding in a unified manner. Moreover, all previous methods on this task can only generate predictions at a quite low resolution, which is 0.4 meters or lower. They also usually requires a post-upsampling to achieve its full resolution or the same resolution as its GT. So in this paper, here are our contributions. The first contribution is we present a high resolution 3D semantic occupancy dataset, nuCraft. It offers 8 times higher resolution and more precise annotations than all previous benchmarks. The second one is we provide a general and robust data generation pipeline for creating high quality 3D semantic occupancy GTs. So and we verify its effectiveness on Vimo and semantic KT. And our pipeline is very robust to noises in the data, and our pipeline generally requires no human efforts. So it's an auto labeling pipeline. And third one is we present a novel 3D occupancy prediction framework, which is VQ-Occ. It decouples the encoding of GT occupancy and the task of semantic occupancy prediction, so we can achieve direct high resolution prediction and also achieve the SOTA performance. So now let's talk about the creation of nuCraft. The creation of nuCraft mainly divided into 4 steps. In the first step, we need to remove all the moving objects, and the second thing is that the sequences in original nuScenes dataset is quite short, but we can find some way to link continuous logs or continuous scenes together to achieve a longer scene. Yeah, here we call it a continuous scene grouping, CSG. And in the second step, we do post estimation mainly to the Z poses of the nuScenes ego car. This enables us to achieve better alignment effects. So for example, on the left side, you can see we use the original ego pose information of the nuScenes to aggregate LiDAR sequences, but the result is very bad, especially in the Z axis, because in nuScenes it eliminates the Z pose. That is, they set the Z axis ego pose to 0. So this can cause severe misalignment in the vertical axis. So after we do this, we can provide a much more clean and much more precise aggregation results. And the third step is we use aligned LiDAR point cloud to do a semantic mesh reconstruction. Here on the right figure, we can see that the top figure is a BV of our aggregated LiDAR point clouds, and we can see that there are many misannotations or inconsistent annotations and some noises in almost everywhere. And we propose to do a semantic mesh reconstruction, which consists of 2 parts. The first part is mesh reconstruction, which means we can fill in almost all the holes in the original LiDAR point clouds. And the second thing is we add a semantic prediction branch to mesh vertices, and this branch can help us greatly suppress the noises and the inconsistent annotations in the raw point cloud. We can see that here the inconsistent point cloud annotations and the noises are all eliminated in the reconstructed mesh. So with this mesh in in hand, we can do the final occupancy GT generation and necessary post-processing such as hole filling and floating mesh removing and so on and so forth, as well as the visibility mask for camera views and for LiDAR. We also validate the quality of our generated nuCraft dataset. We try to evaluate its ability to preserve information in the raw compared to the raw data in the nuScenes. Here the input of our data generation pipeline is basically all available annotations from the nuScenes dataset. For example, the 3D boxes, the point clouds, semantic annotations. So now for the foreground and background, we try to evaluate its performance to preserve information. So we do the 3D object detection on foreground and the drivable area segmentation on background to see how well the foreground information and background information are preserved. We also add all the components of our data generation pipeline to see the effects of each component here. Okay, now let's talk about our occupancy prediction method, which is VQ-Occ, vector quantized occupancy prediction. So here is a diagram of our method. It's basically split into two parts. The first part, we are doing an occupancy GT encoding. In this part, we are using a VQ-VAE to encode the original occupancy GT into a discrete occupancy codebook, and use the codebook and train a decoder to recover the occupancy. And once the occupancy GT encoding is done, we can see that we have already compressed all the GT occupancy into a fixed number occupancy codebook Z. And then in the second step, all we need to do is to process the input to get a certain feature in a 3D or BV feature space. Then we just need to learn to do the feature simulation towards the occupancy codebook. So this is the basic idea. In this way, we can decouple the occupancy prediction into a GT encoding and feature simulation. Each step is much more easier than the original 3D occupancy prediction task. In this way, our VQ-Occ achieves better occupancy prediction performance, and it can also achieve direct predictions of 3D semantic occupancy at a high resolution and the same resolution as the input, so it requires no post-processing. And here is the result of our method. We compared our method in all input modalities, including camera only and LiDAR only, and camera and LiDAR multimodal fusion. And we compared our VQ-Occ with all previous methods on the on previous best open occupancy dataset and our nuCraft dataset at 0.2 resolution. And we can show that our VQ-Occ can outperform all previous methods at all benchmarks at all resolution for all categories. So it's a very promising and a very promising method. We hope our work here can serve as a baseline and a new benchmark for future research on this task to achieve the truly unified 3D scene understanding. Thanks for your watching. Here's all the presentation. Yeah, bye-bye.